Hey everyone, and welcome. Today, we're going to dive deep into electrochemistry. The hidden force that's pretty much powering our entire modern world. And it all kicks off with a simple question.
I know. It sounds like the start of a really weird joke, right? But this question actually gets right to the heart of what we're talking about today. One of them is this amazing piece of high-tech wizardry we can't live without, and the other is just a simple sign of decay. So what on earth could be the connection?
Well, the answer is that both your phone battery and that old rusty nail are perfect, everyday examples of electrochemistry in action. See, they're both all about this fundamental trade-off, this great energy swap between two totally different forms of power.
At its very core, electrochemistry is the science of this swap. It's all about how chemical energy, that's the energy stored up in the bonds between atoms and molecules, can be turned into electrical energy, the flow of electrons. And, just as important, how we can flip that switch and reverse the whole process.
And this slide really breaks down that two-way street perfectly. On one side, you have spontaneous reactions. They just happen. They naturally release electrical energy. That's your phone battery powering down as you use it. But on the other side, you've got non-spontaneous reactions. These guys need a push. We literally have to pump electrical energy in to make a chemical reaction happen. And that's exactly what you're doing when you plug your phone in to recharge.
Okay, so we know this energy is being swapped back and forth. But how does that electrical energy actually move from point A to point B? Well, it all comes down to two opposing forces, conductance and resistance.
I love this analogy because it makes it so clear. Think of conductance as a wide-open racetrack for electricity. The path is clear, the charge can just flow super easily and quickly. Resistance, on the other hand, is like someone decided to throw a bunch of hurdles all over that track. It's basically anything that gets in the way and slows down or even blocks that flow of charge. So who exactly are these runners carrying all this charge? Well, it actually depends on what kind of racetrack we're talking about. Turns out there are two main types of charge carriers, and where you find them makes all the difference in the world. Okay, so let's break this down. In a metallic conductor, like a regular copper wire, the charge is carried by these tiny, free-flowing electrons. It's a physical process, pure and simple. No chemical changes happening at all. But in an electrolytic conductor, like salt water, the runners are way bigger. They're ions, charged atoms. And in this case, their movement is a chemical reaction. And here's where it gets really interesting. Check out what heat does. If you heat up a wire, you just create more chaos, which actually slows the electrons down. But if you heat up a solution, you give those ions more energy, helping them move faster and increasing the conductance. Wild, right?
So let's zoom in a little bit on those solutions, the electrolytic conductors. Since their ability to conduct electricity is a full-on chemical process, it means we can actually influence it with a few key factors. All right, the absolute key player here is something called an electrolyte. This is the stuff you dissolve in a liquid, like water, that breaks apart or dissociates into those charge-carrying ions we were just talking about. If you don't have an electrolyte, all you have is a liquid that won't conduct a thing.
But here's the thing. Not all electrolytes are created equal. You've got your strong electrolytes. Think table salt. When you put them in water, they completely fall apart, releasing a ton of ions to carry charge. So of course, they have really high conductance. And then you have weak electrolytes, like acetic acid, which is the stuff that makes vinegar sour. They're a little more, shy. They only partially break apart, so they produce way fewer ions and, as you'd expect, have much lower conductance. Okay, now this next part is super important, and honestly, it might feel a little backwards at first. When you dilute a solution, meaning you add more water, you're actually giving the ions more space. They're not so crowded, they're not bumping into each other, and they can move around much more freely. And all that freedom means the overall conductivity actually goes up. It's like giving each runner their own lane on the track. More freedom means more speed.
And all of this leads us to a really, really cool scientific puzzle. We know strong electrolytes are great conductors and weak ones, not so much. But what's the absolute maximum potential of one of these weak electrolytes? I mean, how do you measure something that seems to be holding back on purpose? So here's the catch. If you were to plot the conductivity of a weak electrolyte as you dilute it more and more and more, you'd see the conductivity keep going up. But the curve never actually reaches its theoretical maximum on the graph. It just keeps getting closer and closer, but it never actually gets there. So you can't just measure it directly. You need a clever workaround.
And that clever workaround is this incredibly elegant idea captured by something called Kohlrausch's law. It basically says that at infinite dilution, that theoretical point that we can't actually reach, the conductivity of any electrolyte is simply the sum of the conductivities of its individual positive and negative ions.
Let me walk you through how this magic works. So, we want the maximum conductivity of our weak acetic acid, but we can't measure it directly. We know, though, that it's made of an acetate ion and a hydrogen ion. So, what we do is we find the conductivity of that acetate ion from a strong electrolyte that we can measure, like sodium acetate. Then we do the exact same thing for the hydrogen ion, maybe using hydrochloric acid. And then we just add those two values together, and poof, we've calculated the maximum potential for our original weak acid. It's that simple and that brilliant.
I mean, how cool is that? It's such an elegant solution. It lets scientists calculate a value that's impossible to measure in a lab. It's basically like solving a puzzle by using the pieces you can see to figure out the exact shape of the one you can't.
And that really leaves us with a bigger question, doesn't it? This whole principle of understanding a complex system by just understanding the independent contributions of its simplest parts, that's an incredibly powerful idea. Think about it. From economics to ecosystems, what other big, messy problems could we solve if we just found the right way to break them down? Something to think about. Thanks for joining me on this one.